Knowing where high or low pressures exist is a fundamental part of meteorology and safe flying. High and low pressures determine the movement of air horizontally, and to a lesser extent, vertically. The horizontal movement of air is more simply understood as wind. The vertical movement of air is a major contributor to the formation of clouds. So, as you can see, understanding these pressure systems is an important part of meteorology, and as such will be discussed in more detail later on. We have talked about how these pressure systems can move and develop over time. This can be presented on another type of chart, and instead of using isobars, we use isolobars. These lines join places of equal pressure change, or tendency, during the 3 hours preceding the time of observation. These charts are very useful in showing how rapidly the pressure is changing in an area. Regions of falling pressure are shown by closed concentric negative value isolobars. These are called isolobaric lows. Conversely, regions of increasing pressure over time are shown by closed concentric positive value isolobars. These are called isolobaric highs. The knowledge of pressure change becomes important later on, once we have an understanding of the significance of falling or rising pressure. Returning back to the surface pressure charts with isobars, we mentioned earlier in the lesson that there tends to be different spacing between the isobars in high and low pressure systems. The spacing of these isobars is significant and will tell us information about the strength of the pressure variation in a region, and hence the wind strength. This relationship is very similar to contours on a map. The spacing of contours on a map tells us information on the gradient of the land where mountains and valleys are located. We know that tightly spaced contours show a very steep gradient or slope. Similarly, isobar spacing shows the pressure gradient. Tightly spaced isobars show a very steep or strong pressure gradient. We call this force the pressure gradient force, or PGF. A large pressure gradient force means that there is large pressure change over a small area. The pressure gradient is important because it controls the velocity of air, such that if the isobars are tightly spaced, there is a large pressure gradient force and therefore strong winds. Going back to pressure systems, remember that generally in high pressures, the isobars tended to be further apart than in low pressures. This means high pressure systems have less of a pressure gradient and are therefore associated with lighter winds than low pressure systems. This concludes the analysis of horizontal pressure change. We will now look in more detail at the variation of pressure with height. Earlier on, we saw that pressure decreases with height in the atmosphere. In fact, it decreases at a decreasing rate. However, pressure does not decrease everywhere at the same rate. This is because temperature affects the pressure lapse rate of the atmosphere. Cold air has a tendency to cause pressure to change more rapidly over a given height than warm air. Looking at the diagram of the atmosphere from a side view, we can see that pressure is decreasing with altitude. We start at the surface at 1000 hectopascals and reach 300 hectopascals at 30,000 feet. However, when the air on the left is cooled, we can see that the isobar levels start compacting and sinking towards the cold air, This has the effect of reducing the pressure at any given height. Look at the pressure now at 30,000 feet in the cold air. It is no longer 300 hectopascals. You can see the pressure is much less now. We can summarize to say that cold air causes isobars to compact in the vertical, increasing the pressure lapse rate and reducing the pressure even more at any given height. Now let's look at how warm air changes the pressure lapse rate. When the air on the right is warmed, we can see that the isobar levels start expanding away from the warm air. This has the effect of increasing the pressure at any given height. Look at the pressure now at 30,000 feet in the warmer air. It is no longer 300 hectopascals. You can see the pressure is much higher now. In summary then, we can say that warm air causes isobars to expand in the vertical, decreasing the pressure lapse rate and increasing the pressure at any given height. It is important to note that pressure is still less than at the surface, but depending on the temperature of the air, the relative pressure at a given height in cold air will be less than in warm air. The fall of pressure with height can be seen in the table. Note that pressure decreases at a decreasing rate through the atmosphere. A height change of 5 kilometers near the surface reduces the pressure by approximately 473 hectopascals, whereas a height change of 5 kilometers above 25 kilometers reduces the pressure by only 13.6 hectopascals. The values in the table correspond with ISA. We have just seen that changes in temperature and pressure at any given point in the atmosphere affect the pressure change with height. This pressure lapse rate as we know it will change markedly if temperature variations in the atmosphere exist. In the previous example, we have seen how the pressure lapse rate changes with height. An alternative view is to see how height change varies with a given pressure value. In other words, what increase of height corresponds with a fall in pressure of 1 hectopascal. There is a numerical method of calculating the vertical height change per hectopascal. The formula is shown in the diagram. When the variables are inputted into the formula, the result will show the height, in feet, represented by 1 hectopascal change in pressure. The variables are temperature in Kelvin and the pressure in hectopascals. The value 96 is a constant. Let's now see the result of inputting the ISA conditions at mean sea level. For the value of T, remember ISA states that at sea level the temperature is plus 15 degrees Celsius. To convert to Kelvin, just add 273 to this value. Now we have 96 multiplied by 288 degrees Kelvin. The pressure at mean sea level, according to ISA, is 1013.2 hectopascals. The result now shows that a change in pressure of 1 hectopascal at sea level in ISA represents a height change of 27 feet. Let's now observe the result if the temperature is changed. Remember that if we cool air down, the isobaric surfaces or pressure levels compact. Therefore, a change in 1 hectopascal will represent a smaller height difference. If we now insert a reduced temperature of 260 degrees Kelvin, as opposed to 288, then a change in 1 hectopascal now represents only 25 feet, not 27 feet, just as expected. Again, we can confirm that cold air increases the pressure lapse rate. The implication of this temperature effect on pressure variation is very important in producing accurate pressure information. We have seen that pressure varies in two dimensions, horizontally and vertically. To understand how pressure varies horizontally, we would have to remove the vertical pressure variation. As a result, we would have to assume a level horizontal surface. Pressure values which are not on this common surface will have to be adjusted to it. This common level is usually mean sea level. However, as we know, not all surfaces are at mean sea level. Looking at the diagram, we can see a location approximately 1,000 feet above mean sea level. How do we then calculate what the sea level pressure might be? We know that the sea level pressure will be higher, but by how much? This will surely depend on the vertical pressure lapse rate. But we have just demonstrated in the previous scenes that different temperatures will give different pressure lapse rates. If the air at the location was colder than ISA, we would expect the pressure lapse rate to be greater. So when adjusting the surface pressure to mean sea level, we would gain more pressure in 1,000 feet than if the air was warmer than ISA. The two diagrams confirm this for us. The diagram on the left shows that if a station was above mean sea level and the air was colder than ISA, the corrected mean sea level pressure would be higher when compared to warmer than ISA. These mean sea level pressures are known as QFF values. QFF is therefore the barometric pressure at a stated location, corrected to mean sea level, using the prevailing temperature. How are these values used though? Well, firstly, they are plotted on charts and then lines are drawn, joining places of equal values. These lines, as we already know, are called isobars. Isobars on surface weather charts are therefore derived from QFF values. These surface pressure charts are commonly seen in weather broadcasting and weather briefing information. As you can appreciate, pressure is fundamental in meteorology and aviation. Throughout this CD-ROM, pressure is mentioned and discussed many times. It is important to understand what it is and what affects it. As you can appreciate, pressure is fundamental in meteorology and aviation. Throughout this CD-ROM, pressure is mentioned and discussed many times. It is important to understand what it is and what affects it. In the lesson on pressure systems, you will see how important horizontal pressure variation is in understanding weather and wind. In the lesson on altimetry, you will see what significance the vertical pressure variation has on aircraft operations and procedures.